Well, good afternoon, ladies and gentlemen. Welcome to another in our series of seminars in the I for Energy program. Glad you could be here, and welcome to our viewers on the web, especially from our sister campuses at UC Santa Cruz, UC Davis, and UC Merced. I switched the order of those around for all of you on those campuses just to be fair and not always do it in alphabetical order. I know I'll hear a complaint about that. My name is Gary Baldwin. I'm the Director of Special Projects for Energy and the Environment here in CITRIS. Before we begin, I wanted to call your attention to some flyers that we've left on the back table announcing a talk by Christina Johnson, who is the Undersecretary of Energy in the U.S. Department of Energy. She'll be here next Tuesday, October 7th at 12 noon in 290 Hearst Memorial Mining Building, speaking on the topic of energy challenges facing our nation and how the Department of Energy is addressing them. I would suspect that that's a topic of great interest to a lot of people in this community. So I urge you to go and hear Secretary Johnson's comments. Today is our very great pleasure and honor to welcome Dr. Carsten Westergaard from the Vestas Wind Technologies Company. Carsten is becoming a good friend of CITRIS. Vestas is sponsoring a project here already. We look forward to a long and productive relationship, and it's been just delightful getting to know him and getting to know some of the ideas behind this growing emphasis on wind turbines, all of the problems that one faces and all the opportunities that one has. Carsten earned his PhD in the 90s at the Danish Technical University. He studied optical computing and optical flow measurements, fluid mechanics. Part of his research was also completed at University of Illinois in Champaign-Urbana. He started his career in wind technology as an aeronautics blade designer, hence the transition to wind turbines, and has been working with fluid and structural dynamics in many different industries. He joined Vestas about 3 years ago. And Carsten, it's wonderful to have you here today. We look forward to your comments, and let's welcome him to our seminar.
Thank you. It's a pleasure to be here, and I hope I can live up to your expectations. I will talk something about wind technology, manufacturing of wind turbines, and the technologies and the logistic changes that go behind deploying wind. I'll try to relate a little bit to innovations and also to the challenges that we see ahead in the wind market. First, a little history lesson. In the turn of the century, there was a lot of work in Northern Europe, specifically on wind, actually. And this is the Danish inventor Paul Lacour that was experimenting with wind turbines, and it was called windmills at that time. And he had some very strong visions about how wind turbines could help the rural areas and produce electricity in rural areas and keep people in the rural areas because there were problems in the cities. He didn't call them windmills, he called it a wind power plant, and was trying to produce a lot of energy, as much energy as possible. Did some quite advanced for the time being. He had a little wind tunnel trying to optimize his wind turbines. And also the energy was stored by hydrogen, by liquid hydrogen, by electrolysis, and then the hydrogen was burned at nighttime at the campus of the school that he was working at. And this was sponsored by the Danish government, actually, as a research grant. So it's actually started quite early. We are facing increasing energy demands whether we like it or not. And obviously that can have consequences to the world. And it also calls for challenges. Well, this thing here is not working. Okay. Oh, here we go. So we see energy resources being emptied out, and also we see some challenges coming ahead with that. So this basically calls for a challenge. We need new energy sources, and we need more of them. And we also have the climate dilemma. I'm not going to talk about that today. You have lots of good people here at Berkeley working on that. But together with the rising energy demand, we also have the CO2 emission issues that needs to be addressed. So if we're looking for a future, we also have to look at what kind of resources can we harvest. And it has to be competitive because it has to go into a modern society. We have to be able to deploy it. We would like it to be clean. We would like it to be renewable. But it also has to offer the independence. And wind has these elements in it inherently, because wind is free, as you know, and also we are capable of deploying wind relatively rapidly. And that's also why I want to talk about the logistic change in wind here today. So actually ramp up is actually an issue when you think about meeting the challenge of future energy needs. Just for a calibration, a Vestas 3 megawatt turbine produces roughly 75,000 barrels of oil a year equivalent. And it does that without any consumption of water, and it does that obviously without any production of CO2. Vestas has a slogan that's called wind, oil, and gas, and a lot of people question this slogan. Why do you have that? Why do you want to? Why do you see that together, wind as oil and gas? And what we're trying to reflect here is that wind has to be perceived on par with oil and gas in order really to have success. We have to get wind into the energy system on the same terms as all the other energy sources that are in the system. And we have to do that in order to be responsible and deliver responsible energy to society. We cannot just deploy very expensive technologies and just expect society to pay and prosper from that. Society has to prosper. Society is prospering from oil and gas today and has prospered from that, having energy that way. So we have to be on par with that to have success. The key to that, we call wind modern energy at Vestas. We don't call it a renewable, we don't call it alternative. And again, this renewable and alternative are often associated with expensive. So again, which is far from the truth when it comes to wind. So again, we are trying to say this is an alternative source. It is on par with oil and gas. A key to delivering a cost-effective energy and a cost-effective machine is obviously technology and R&D. So that's what we do, and that's what I do in my daily work, and that's the purpose of Vestas technology. A short little detour. Vestas in North America has a very large number of locations. I'm from the Houston office that we're establishing, which is a research office. Our headquarters for Vestas Americas is in Portland. It's a sales and operations office. And we're building factories in Colorado right now as we're speaking to deploy wind in the U.S. And then we have a very large number of service warehouses and service people around the United States to service our turbines. So deployment is very important, and right now we are building, we have one factory operational, we're building the other 3 factories here in the Denver area. And we're investing heavily to be able to deploy wind and meet the visions and goals that the United States has put out. We have big expectation for that. And we expect by the end of 2010 that we will have 4,000 people directly employed in the U.S. working on deploying wind turbines. And that's just the direct employees in Vestas. With that comes a very large number of sub-suppliers and service and maintenance later on in the lifetime of the turbines. So it's also a big commitment to workforce development. Very shortly, just to understand Vestas as a company, we have our geographical organization, we have our production units, and I'm from the technology division, which develop our turbines and do research into the future of wind turbines. So What has happened over the last 25 years? Vestas had its first adventures here in California with some relatively small turbines, but in the meantime, there's been a lot of technological development. And in this, I think it's illustrated quite well that the size of the turbines has grown to become quite big, much bigger in size. Basically grown from something that was a 15-meter rotor to today we are building on our V112, so it's a 112-meter diameter rotor, roughly the same tower height, 3 megawatts of energy produced. And we do this in a very cost-effective way, in a reliable way, and with lots of technology inside it. So I'm going to talk more about the technology that's inside the turbine and some of the challenges here. We have roughly 35,000 turbines around the world that are operational. About a third of them we have monitored 100% online. We can log into each and every turbine and see what it's doing anywhere on the planet. So we know a lot about wind. Very fundamentally, a turbine is operating outside in nature, and what you have to challenge is you have to basically take the loads off the wind, convert it into electrical energy. And many times we get association from wind turbine technology to aeronautics, maybe to helicopters, and maybe even to building structures. What this is trying to illustrate is the number of cycles, so the fatigue on any component in a wind turbine that it sees in its 20-year lifetime. And then the complexity, typically in bicycle here, is a very regular loading that you get from pedaling in a relatively slow pace. So in its lifetime, it sees a relatively low number of load cycles. A wind turbine is outside nature. It has, by sheer the stochastics of the wind, is hitting the turbine, and it receives a very large number of cycles. So the material is really working hard in a wind turbine, and you have to design that for the 20-year lifetime. So that's a key challenge, to make materials and understand the materials and project the lifetime for 20 years. The complexity of the machines has obviously also risen during the 25 years we have been building modern turbines. This being a V10, very early days, so very simple generators, blades, relatively simple towers, and relatively simple machine. Today, the machines are very large. They have a lot of sophisticated equipment in the sensors, computers, sophisticated materials in the blades, a lot of materials handling concerning all the steel that's used for a turbine. This is a V90 machine. The load comes in here through the rotor from the composite blades. The blades are sitting on bearings, so the blades can be turned into the wind, similar to the way you regulate a sailboat when you're sailing. There's a gearbox, there's a generator, there's a step-up transformer that transforms the power from the generator into something that's usable in the local area grid. And this has an area roughly the size of a soccer ground. So it's a very large area you're harvesting. It runs in very high wind speeds. A lot of people ask, why does the turbine shut down at high wind speeds when there's a lot of energy to be harvested? There's no need to run there. It happens very, very rarely out of the year. If you run at those very high wind speeds, you're fatiguing your materials, so the cost benefit of doing it is not really worth it. So you might as well shut down. So it's not because you can't, it's just not cost beneficial. A rotor weighs 41 tons. This is being transported typically 1,000 miles out to the sites. Nacelle, 70 tons. It has to be lifted up 300 feet. And the tower in itself, about 300 tons of steel. And to that obviously comes the foundation, so the whole thing doesn't fall over. Roughly during a year, a turbine like that produces energy for 3,500 households. So what do we do at Vestas? Well, obviously we do the research and development. We manufacture the turbines. We assemble them on site. Prior to actually developing your wind turbine projects, you go out and you evaluate the site. You measure the wind speeds for typically over a year from a metrological mast you erect at the site. But in addition to that, we also go in and we do a detailed evaluation of the landscape and the effects that the landscape has on the turbines, both from a production technological perspective, but also from the perspective of how the turbine is loaded by the wind and the landscape. We do transport, and there's many challenges in that. Put them up, and obviously also we have the maintenance and monitoring of the turbines. So it's a long value chain just in our company, and then there's obviously also all the development of sites, which is done typically by wind developers. They develop the sites, identify the sites, do the metrological measurements, and then you move on, and then into the operational system. We made one of these turbines, so a 300 feet tall turbine, somewhere on the planet every 4th hour. So you can imagine moving all this material, all this from our different factories to the sites, getting them operational, and then service and maintenance. It's a big logistic change, so there's a lot of emphasis on doing that efficiently, cost-effectively, and reliable. And this is done outside, and this I love this picture because it shows some of the challenges in a very simple way. We have turbines in deserts, open plain fields, mountainous regions. It can snow, it can rain, it can hail, it can be lightning, it can be offshore. There can be all kind of weather phenomena around the turbines. And we have to deal with this over a lifetime of 20 years. So a lot of experience goes into the design of a turbine, a lot of experience in operation, and a lot of experience in maintenance, and a lot of experience in commissioning, getting out there in the right weather conditions. This is an example of a landscape evaluation I was showing before. We get maps and we take it into advanced computational fluid mechanics computation, and we evaluate the landscape as a part of our process to make sure that the development of that site has been taken care of in a responsible way. We also develop our own blades and airfoils, and we go to wind tunnels, we test the blades, we test the data. This is a wind tunnel picture of such a test. Here's a picture of what it could look like in real life. This is typically what's happening after it's been harvest going on. Then there's a lot of dirt in the air, and that accumulates, and it rains off a couple of days later when there's rain, and it cleans. So this obviously influences the performance of the machine. So it's important to understand the real operating conditions. This is manufacturing. So you can imagine you have to get these out the door every 4 hours. You have to have 3 blades for each turbine. So our manufacturing is typically a serial production with several lines in each factory, so we can deploy the turbines efficiently. This is the finish hall, where you take you close the finishing of from the molding process of the composite blades. All blades undergo testing and certification before they are put out there. We put a lot of emphasis on testing our products. We have a lot of in-house testing, and we also use external testing facilities in many cases. So this is a static test, and you can kind of see here the bending. This is the bending that we do in order to make sure the statics of it is okay. The blade is also tested for fatigue. So it undergoes an accelerated fatigue test, which is typically taking somewhere between 3 and 6 months time, where the blade is oscillating with very large amplitudes for 3 to 6 months to make sure that the lifetime of the blades are adequately at rest. Transportation, train transportation. This is preparation for shipping with ships. So, and there's a lot of aspects of transportation. Transportation is an important cost in wind deployment, actually. So you can imagine. And this, now you can maybe see the point of the Colorado facility. We can load onto the trains directly from the manufacturing there. You have to get out there. It might be snow, it might be rain, and you have to get blades up there. You have to put it up with the hub, which has all the hydraulic actuators that can turn the blades and move them in, either for regulating the power or to stop the turbine. The drivetrain, this is our drivetrain test facility in Aarhus in Denmark. So this is where we take the gearbox, the generator, place it in a drive test facility, and also test it for wear and tear many months. It's done so with the electrical systems that goes behind the drivetrain. So there's a lot of again, a lot of testing to ensure the reliability of the products are adequately met, and we can deploy it safely into the market. Innovation, things that could potentially be perceived as very simple. If you have to service a turbine in the middle of nowhere, first of all, when you build a project, you have to build a lot of infrastructure, typically roads to have access to the site. Going, say, across a field, you have to make sure that you have the roads, you have the infrastructure, obviously for the grid and the connectivity and all that stuff. But you have to have trucks there. But once the project has been closed down, the turbines are operating, they're out there by themselves for 20 years. You have to go back and you have to service a main component. Suddenly you have to reopen that road, get a 100-ton crane out there to lift down a big piece of equipment. Very costly and very complicated and not very efficient. You might have waiting time to get the crane out there, et cetera, et cetera. So innovations like a crane that can crawl up the towers without scratching the paint, lift down a major component to the ground, being serviced, put back in operation. Very important. I forgot the reference, to put my reference on this picture. It's taken by a service company that flies out to the offshore platform in the North Sea. But it's taken at the dew point of the sea, as you can see, and you can here see the dew point, and you can see turbines. It's Horns Reef, Vestas turbines in Horns Reef in the North Sea. You can see the complexity of the turbines operating in parts. And this is ongoing research, and it's obviously very difficult and very challenging research to deal with. We have lots of experience in operating in these conditions, but understanding the environment is a completely different story to understand that in a scientific sense. One of the key barriers for wind is actually transmission. Deploying wind is often happening at remote sites where there's lots of wind. We have to get the turbines, and my apology, I had a whole row of turbines here. I don't know what happened to the rest of them, but all of these have to tie into some substations, get into the grid, get into the local area, get into larger transmissions, and get back into the large transmission system in order to actually be deployed into cities. So this is a major barrier for wind, actually, the infrastructure in the transmission system and the capabilities of absorbing other sources than the classical power system. And it has something to do with the way that the systems are generally designed. Here you are designing a power plant to have a base load that feeds into the system and going into a variable pull from the consumers, where the wind has obviously a variable input to that equation. So there's some experience and operational parameters that is different operating the grid system than there is in the classical sense, but in a traditional grid system. Part of what helps the operators is that they have all their turbines online, so they can go in and see what each and every turbine is doing, and they can see what sensors are giving back, what is the temperature of a gearbox, what are the different electrical conditions. All of this is monitored online from the operator system. So they can operate this as a power plant and put that into the system parameters that they have to operate the grid. And they can pull data back from the turbines. What are they doing? How are they performing? And so forth. To give you an idea about the variability that is in wind, each of these little dots that you see on this plot is a 10-minute average value. So you can see there's a certain scatter around that. So that gives you an idea about the variability that one have to deal with in a stochastic invariance that one have to design up to. Offshore winds. This is an assembly site in a harbor that is deploying offshore wind. And it's you can kind of sense here that the deployment, again, the logistics of deploying wind into offshore requires a lot of space. It requires a lot of infrastructure. It requires harbor basins. It requires ships that can deploy all of these components. Salem offshore, you can see some of the ship and some of the equipment that's used to lift the turbines up, assemble them, and put them out at the site offshore. There are advantages of putting wind offshore. Main thing is there are obviously more wind resources. They're stronger, so there's more wind to harvest. So you have a better income from the machine. There are also some other issues that are lower turbulence, generally speaking. There's generally less resistance from the local population when you deploy wind, especially in Europe. On land, there's usually relatively close to population centers, so there can be some local resistance. Transportation is actually a plus here because you have no weight limits, generally speaking. Offshore technology is generally very heavy, so weight in itself is not an issue. That's an issue on land when you have to transport things in trucks on small roads, etc. But also has some disadvantages. You have to deal with very, very complex site conditions. You have waves, you have the geology, you have sand waves, you have saline environment, and also you have the complication of service and maintenance. You cannot just go out there when you want to. If there's waves, you cannot access the machine. You cannot dock a ship up to a fixed structure in the same way. If you compare to the offshore industry, the platforms, for example, in the offshore drilling industry, is much, much larger, so they're not affected in the same way. So access is an issue. Here's some picture that can give you some of the impressions of some of the challenges in deploying wind offshore. This is a monopile that's been ramped down. There's a fairing that sits on top of the monopile that's been ramped into the sea floor, leveraging the turbine and providing the first access to the turbine, the tower being mounted. Later you mount the top of the turbine, and then you mount the last blade. You can see the deployment ship there. So this ship has a couple of turbines, sails maybe for an hour or two out to the site, deploy the turbines it has on site, go back, pick up more, and so forth. So if you think about the deployment rate that I was talking about earlier, maybe you can also see the deployment rate is different in an offshore environment. And obviously it's windy offshore. So this is a real picture taken of the same wind park as I showed before, Horns Reef. It's taken from one of the helicopter pilots that flies out to the offshore platforms in the North Sea. But you can see very large waves. And, you can see a turbine here that has to survive this kind of environment. But they're obviously designed for it, and that's what we do for a living. Lightning, also stronger offshore, generally speaking. Very strong lightning is another issue, something we also have to deal with. So where does all this take us, and where are we today? These are some numbers from the European community. Denmark actually has now exceeded 21% of wind, and are still going forward. So we have 20% wind. We don't have any advanced storage capabilities in our network. We do not have any advance. It's simply operating the wind. We have days with over 100% wind in Denmark and are able to manage that into our electrical system. Spain is very far progressed, Portugal, Ireland, Germany, US on average. Currently or 2007 there was about 56 gigawatts of wind in Europe. About 1 gigawatt of that was offshore. The annual investment, this comes out of a European report that you can find online. The annual investment is roughly 11 billion euros a year in deploying wind. And if you look at the visions for Europe, this is roughly what is required. So something of 12 billion euros a year that needs to be invested in order to deploy these kind of wind scenarios. This is the envisioned installed capacity. The blue here is offshore. This is the annual cost. So the green is correspond to that. That's the cost. So you can see offshore is more expensive, but as I said earlier, the payback is also higher. So there's a balance there. There's more that has to be optimized in the offshore environment. And this is what this costs. So this is the installed cost according to the European Wind Energy Association. So this is the land-based cost curve, and this is the offshore-based cost curve. So this is thousands of euros per the kilowatt. So the rating of the machine. So obviously, in order to bring this down to a cost-effective scenario, we have to work very hard on the cost of energy. And that's what we do at Vestas. This is the scenario that has been put out from the Department of Energy. 300 gigawatts installed by 2030 was the vision put out in that report. In the US, it's 54 gigawatts of offshore envisioned, mainly along the northwest coast, northeast coast, some in the middle, and a little bit in the Gulf. So, and that's a balance between the proximity to the big cities, and then the big wind belt. The U.S. has a lot of land in the middle, as you know, and there's a lot of very nice winds there. So, but there's not so dense population, so you have to have transmission to get the wind deployed there. Texas is one of the very progressive states. They have very far in implementing wind, and they're building transmission lines up from the Panhandle, so the Midwest, into the big cities, deploying 8 gigawatts of wind over the next 4 or 5 years. And they already quite a lot of. I think it's about 3.5% of wind. There's penetration in the Texas system, in the ERCOT system. So they're quite well progressed in Texas. So what are the challenges in deploying wind? And according to the report, like I said before, investment in the transmission systems, and this is now coming online. There's a lot of work going on in investing in transmission in the U.S. There's also a lot of deployment looking at how can the grid be used smarter. So smart grids and I'm not going to talk about smart grids today. Smart grids can mean a lot of different things. Anything from deploying into the grid to taking off the loads from the consumer in a smarter and more intelligent way. Storing energy on cars is one of the ideas. Electrical cars, is you have cars taking energy off the grid at nighttime when there typically is not a big load, but you can have the renewable sources producing at night, where you normally take down the production from the classical power plants. They ramp down during nighttime when there's no need for it. So there the renewable sources can produce at full speed ahead. At least the wind can, the solar can. Obviously it's during the day. So the balancing of all this is very important. There are some challenges in technology. As you can see, this is not the number one challenge, but it is still nevertheless a challenge. And you can see manufacturing capabilities and performance through technology, as I have illustrated maybe also through my talk, showing you some of the logistic challenges that you have in deploying wind. And then addressing local concerns about sites. We've gone through this in Europe many times, but there's definitely also issues in the US to address these things. I put this in a little bit of difference here. So basically, we've boiled it down. It's understanding the wind environment, as I've also shown some of the things that are needed to be understood. Wind at high heights, wind in parks, etc. Wind from the landscape. Getting things deployed in an efficient way, using the materials efficiently, maybe using newer materials, and then the integration into the system. And that has to do with the farm size, the networking of farms, the forecasting, and the load, managing that into the system. The reliability, as we're working on that, the performance in the supply chain, and then managing the grid and looking at different ways of managing that in a more efficient way. Storage, for example, like I said, could be the electrical cars. What that means for a company like Vestas and what we do in Vestas Technology is we need to bring down the cost of energy. And we need to keep striving to bring that down. And that's basically what our metrics is. That's the only parameter we work on. We want to be competitive. We need to be competitive on par with the other energy sources. That is our only goal in life, to bring that down. That's what we work on. Each and every project we do, we ask this question. If it doesn't bring anything to the table, we don't do it.
Is this cost of energy per turbine or cost of energy over...
We hold the questions to the end.
Oh, sorry.
Yeah, thanks.
It's a cost of the energy that you provide into the grid to the consumer. And it's a ratio. I can answer that back. The way we do it at Vestas is that we work with partners in our research part. So the long lead part of this, we have a lot of partners. We have research centers around the globe. We have obviously in Denmark. We have a research center in Singapore, one in India, one in the UK, and we're building the one in the US. We started that this year. And we work with partners at universities. We engage in research with partners. We engage with projects. And we have a lot of different ways we do that. For example, we participate in the community. We go out and do lectures. We have interns. We have PhD. We have sponsor programs. We do research projects with universities. As Carrie mentioned, we have a project here at Berkeley. So there's many different ways we engage, and we reach out to solve these challenges, and also for the future. So we have very strong capabilities of deploying now, but we also need to keep improving to keep being cost effective. So that was my last slide. Thank you.
Okay. Now we have opportunities for questions. We have one here. We have two microphones. So I'm going to give this gentleman a microphone first, and then I'll get one to you, Dave. Let's use this so that our remote viewers can hear your question, please.
Thank you. What were the circumstances in Denmark that led Vestas to become a leader? Was it business or the history, or what factors were there?
That's a very good question. I don't know if there is an answer to that, but if I should speculate, I think it was, there's a lot of entrepreneurship in the early days of deploying wind. And there was a lot of capabilities in the early days that were simply just applied because it seemed like a good idea. So I think that's one of the factors. The national laboratories research did some very a lot of pushing in the early days as well. I think there's a lot of different factors, and several companies in the Jutland area of Denmark basically developed wind, and it was competing, and it was basically just growing out of there. I can't get it any closer than that, I think.
David.
So I'd like to get a sense of your feeling about the trade-offs with scale. So you had a nice picture of kind of the progression to
the size of the turbine.
Yeah, size of the turbine, the height of it. So clearly from just the physics of wind, there's a big driver pushing you to ever bigger.
Yeah.
But then you also talked about some of the logistical costs.
Yes.
And then, once things become extremely expensive, then you have to be very careful about where you site them. And so it seems like there's some point where there's an optimal somewhere in there.
If I knew the answer to your question, I would be happy to answer it, but I can maybe answer it from a historical perspective. As Gary said, I joined Vestas 3 years ago, but from a historical perspective, I worked in the wind in the early 90s as well. And at that time, basically people said, no, that's it, they can't get any bigger, we can't transport them, we can't do this. And we're still saying that today. So I don't know what the right answer is, but there is definitely a cost-benefit analysis that you have to do for each type of machine that you do, and for which market. And not all machines are designed for the same market, and that's maybe also important to remember. That's why we have different machines, otherwise we would just have one. So the size and the generator and the height of the towers are two main parameters, and we have a lot of variance. So many times the turbine is customized to the site by those parameters, or selected by those parameters, and the wind available, because the wind available at the site is a very important parameter in that.
So could you imagine that there's additional growth at the low end in addition to at the high end?
I think that's possible, especially here in the U.S. It seems like the small wind, I haven't talked about that at all, it's not our business, so, but outside that, I think that there is the small wind, because there's some infrastructure in the U.S. that allows for that. It's not true for every market, and it's not true for every place on the planet. So, but I think, but that's specifically for that end, yes, I think there could be. But it's, again, not my business, so I don't know a whole lot about it. I just know that from the reports that's been done, and so on, from the Department of Energy.
Next question is here.
Yeah.
This is, in a way, the same question, but maybe pushing it a little further. Do you think there's any future for decentralized wind, like, people putting a turbine on their roof the way they put solar panels on their roof?
So, yes, same question, yes, I think there is. And again, in the U.S., I can only repeat what's there's being an environment built where that is feasible. So it's, from other countries, it may not be feasible in the same way. But you have the room, and you have the space, and you have availability of those resources locally. So yes, I would think so.
Yeah. So hardly anyone could be against wind energy, but I have heard, unfortunately, that they, at least in California, maybe some of the older turbines, kill a lot of birds, unfortunately. So what's the progress on that?
So if they kill a lot of birds?
Well, there was a recent article in the, I don't know, maybe it was in the Chronicle, I can't remember, but they even rare predators and stuff like this, they're killing like golden eagles and birds we don't want to lose. So what's the progress on, is there advances where you can somehow discourage birds, the turbines go slower or higher or something? I don't know.
I think there is different aspects of that. All sites are evaluated. So the evaluation of putting wind up is those parameters are going into the site evaluation. So it's taken very seriously. It's being studied at site deployments, and it's also being studied in general. And I don't know anything about the specific that you're mentioning, but it is being studied both in the general aspect and as far as I understand, there are species variations and there are site variations.
Sure.
So, and that's why it's part of a study for putting up wind farms. So it's being taken very serious.
Okay.
But I think it needs also to be put into perspective in terms of what other things that society does to
I'm not saying
to the wildlife, and sometimes I think that perspective is missing from that. I'm not commenting specifically to what you mentioned because I don't know anything about it.
That'd be an interesting curve to see, how much wildlife do the alternatives.
There are lots of reports on that, and a lot of reports that puts it into perspective, and I think you need to put things into perspective. But it is being studied at every deployment, and I think that's important.
Okay. Have you deployed any of these in Antarctica?
No.
And why not?
Well, I think first of all, it's not very close to the load, so the consumption. So we the transmission problem is probably a little bit bigger than anywhere.
Supporting, you can support the
community.
scientific community, and also there's really high winds, and you probably have a different design because it's the amount of power that you can generate is a cube of the wind.
Yeah. That's correct. So there is diesel electrical systems used in some places. In Alaska, for example, I'm aware of that. I'm not a big expert in that, but it's typically related to the question that was up here. The small scale local community that has a diesel electrical system and a wind turbine has had some merits over many years in more remote areas.
Because I was also part about putting it in extreme locations. The problems are that there's also a great benefit because it's a huge cost of bringing energy to those environments.
It's not something that Vestas is working with. We're working uniquely on the large utility scale machines, but it is deployed, and it's also part of the roadmap from the Department of Energy. So it's been thought of by the Department of Energy.
Next question.
Assuming that utility scale storage becomes cost effective, do you see a role for integrating utility scale storage on the wind farm itself? And if so, is that a business that Vestas would get into?
The last part I can't comment to, but the first part is yes. The storage issue is relevant to wind. It is relevant to solar. It's relevant to the grid. Operating the grid, there's a lot of research going on these days on deploying storage to help alleviate the switch points and so on. So absolutely, it can help, and I think it's in some circles, this is also considered a smart grid that you can do.
Specifically, the reason I ask that is that does reduce the cost of energy, and therefore, would that fall under your mission?
We make wind turbines. We like to be good at that, and we like to focus on that part. We're really good at that, and we like to keep staying good at that. The other would be a detour, because I think it needs to go into the whole energy mix. The storage is not just about wind. It has to go into the whole energy mix. It has to go into the operation of the system. So I don't see that as a wind issue per se. Dispatch.
A couple of minutes ago, in response to a question down here, you talked about the cost-benefit analysis necessary as regards scale of turbines.
Yeah.
Could you be more specific on that with regard to the transition from 3 megawatt to 5 megawatt turbines?
Well, generally speaking, when you make the rotor bigger, you harvest more energy, and you can reach a higher megawatt at a lower wind speed. So if you have low wind speed at a certain site, having a larger rotor, you reach a higher megawatt much sooner. So if it's a low wind speed site, you have high wind speed rarely, so there's maybe no point in putting a large generator on that. So that's one side of that optimum. If it's a very high wind speed site where there's a lot of wind in many hours with very high wind speeds, you might want to put a much higher rated generator at the same site. Generator costs money, so it's an economical balance towards that site, and that's again why we have some of our turbines is classified. It's called IEC wind classes is typically what we classify our turbines, and then one is a very high wind speeds, so typically they will have a higher rated generator, and then on the lower end is typical class 2 or class 3 is very low, and probably typically they're very difficult to get financially viable, but those will typically have a smaller generator with the same size rotor. So that's an optimum for the site and to the wind available.
Well, I'm interested again in the scale question. When your example showed the 55 kilowatt machines, but at that time people were attempting to build multi-megawatt machines.
Correct.
And didn't succeed.
That's correct.
Can you explain what happened and why you could succeed and they couldn't?
Well, some of the big machines that were built at that time were built with aluminum. The blades were aluminum. They were fatiguing too quickly. The manufacturing cost was very high compared to the deployment rate that you need. So I think so some of the...
These materials that you're using now were not available, or?
They were not precise. I don't they were probably, I mean, it's glass fiber. At that time, it's glass fiber, so they were available, and they were not considered in those projects. I think those are some of the main failures that were made. There might have been others. I haven't studied that to a large extent, but I know the projects you're talking about, the NASA mod turbines and so on. So, but they use metal blades, and I think that was one of the main points.
Two more questions or so, please.
Hi. A lot of people talk about spreading wind turbines over a large geographic area to sort of compensate for the variability in individual wind. From your experience, is there any sort of, I don't know, characteristic length over which you essentially get wind turbines that are uncorrelated? Meaning, how far do you have to place wind power farms to essentially get them to be uncorrelated?
It's a very good question. I don't know the answer. I wish I knew.
Yeah, one more technical question. So how do you integrate the wind farm generate energy into the traditional power grid? Like what kind of interface do you use? Or is there sort of you have a central location trying to just do this coordination?
I'm not quite, although generally speaking, you have the generator, so we step up the voltage in the turbine, and so it depends on how many turbines you have in that collection, and it depends on what the local grid looks like, how you collect that. But typically it goes to a substation where you step it up again, and then so all the turbines go in with a certain voltage into that step station, and then it is stepped up again into whatever is compatible with the local grid there. So it depends on the site and the transmission available.
We're going to take one more question live and on the air, and then perhaps Carsten would stay around after for anyone that wants to come down and have a further discussion with him. So Shmuel, one more question from you, please.
Yeah, here we kind of, the intermittency of wind acts as a barrier to how far on penetration. What's special about Denmark that you're able to achieve such a high penetration? Do you spill a lot of wind, or do you use the water from North Pole to make up for it, or?
Yes, there's a strong connection in North Pole, as you point out. So that's part of the answer to that. But I think also it has a lot to do with operational experience, basically. So the operators of the Danish utility companies basically have experience from many different sites, and they look at the weather forecast and whatever they do, and they have learned how to operate it into the system in an efficient manner. So I think it's part of the answer to your question is experience.
Thank you very much, Carsten. That was terrific.